So in the previous section, we looked at the solubility of solids in water and found that as temperature increases, generally the solubility also increases. But if we look at different gases, methane, oxygen, carbon monoxide, nitrogen, helium, the solubility of these gases decreases as temperature increases. Another interesting thing to point out that we'll talk about in just a minute here is that the solubility of the different gases is different based on the molecule. So CH4 is a different molecule, is different than O2, but also their solubility is different. But generally speaking, the molecules are more able to escape it at a higher temperature. And you know this from a practical perspective. Soda is carbon dioxide dissolved in water, and warm soda goes flat faster than cold soda. Okay, because the molecules have more energy and they're more easily able to escape out into the gas phase. So this brings us to Henry's law, and Henry's law talks about the concentration or the solubility of a gas in water, and it's related to two things: the Henry's law constant, Kh, and the pressure of the gas. And I'm going to talk about these separately. First, Kh, because it comes first. Kh is a constant for different gases. And if we look at different gases here, nitrogen to ammonia, okay, you'll see that they have different Kh values. And if we look at nitrogen, so I'm going to pick two extremes, it's 6.1 times 10 to the minus 4, which means that since this is a small number, the solubility of nitrogen is relatively low, assuming the pressure is the same. And if we look at ammonia, it's 62, which is way higher, okay? I don't know how many orders of magnitude, 6 orders of magnitude, higher than the N2. Well, why is this? What explains this? What explains this is like dissolves like. Ammonia can hydrogen bond with water, so it's pretty soluble in water. Believe it or not, ammonia is actually a gas at room temperature. The ammonia you buy at the grocery store is actually ammonia dissolved in water. Nitrogen gas is much less soluble because it is completely nonpolar. And there are some drinks that contain dissolved nitrogen. Guinness beer is an example of that. And Guinness beer uses nitrogen as opposed to regular beer, which uses carbon dioxide. And since nitrogen is less soluble, it's less fizzy, which gives it a different taste than beers containing carbon dioxide. So the Henry's law constant is essentially based on the intermolecular forces between the gas, nitrogen and ammonia are two examples, and water. The stronger the intermolecular forces with water, the more soluble the gas is. So like dissolved like explains this. The second terminology here, or the second term in this equation, is the pressure of the gas above the liquid. And this is something that we're not going to talk about in great detail, but this is something you're very familiar with. When you take a brand new bottle of soda, it's not flat. Why isn't it flat? Well, because they've pressurized that bottle and put carbon dioxide in there above the liquid, which keeps the carbon dioxide dissolved into the water, which keeps the soda from being flat. However, when you take the cap off, you reduce the pressure of carbon dioxide above the liquid. Therefore, the soda tends to go flat. Now, some of the carbon dioxide in it will come out and it'll be trapped in the bottle, which again increases the pressure of the carbon dioxide above the liquid, assuming the bottle's closed. So you get away a few times of opening and closing it, but oftentimes when you get towards the bottom of a 2-liter bottle, it no longer has carbonation because there just isn't enough carbon dioxide to repressurize the bottle. So that's basically the two factors. The factor that you would ever be asked about in this class is Kh, okay? So let's take a look at an example here. And as usual, I'm going to switch over to the camera view so we can do that. It says, rank the following gases in terms of increasing Henry's law constant. And then it says, which is the most soluble in water? Well, in order to rank these in terms of increasing Henry's law constant, we need to think about their intermolecular forces with water. So Henry's law constant is proportional with the solubility of the gas. Said another way, the one with the highest Henry's law constant is the most soluble, or the one with the lowest Henry's law constant is the least soluble. So let's look at the type of intermolecular forces that these molecules might have. Now in this case, we don't really need to draw Lewis structures, okay? So if we look at CO, it's got a C on one side and an O on another. They're not the same. This one is polar. Why isn't it hydrogen bonding? Well, it's not hydrogen bonding because there is no hydrogen. So the strongest intermolecular force here is dipole, dipole. Okay, if we look at helium, helium just an atom by itself, all right, and the strongest intermolecular force here is simply the dispersion force. What about ammonia? Ammonia is capable of hydrogen bonding with water, okay? To some extent, CO is capable of hydrogen bonding with the oxygen, hydrogen bonding to the hydrogen of water, but ammonia can more strongly hydrogen bond, and it has hydrogen bonding intermolecular forces. So, if we were going to look at these in terms of the Henry's law constant, which one is going to have, since we want increasing, we want smallest first, the weakest forces, that's going to be helium. And helium is going to be less than CO, which has dipole-dipole forces and some ability to hydrogen bond with the hydrogen of water, but not the oxygen of water, and followed by, finally, ammonia. Which of these is going to be the most soluble in water? Well, the one that's the most soluble is certainly NH3. Why? Because NH3 can hydrogen bond with water, which makes it quite soluble, and like dissolves like.